Everyone was told this object would come and go, a brief visitor, a cosmic stranger passing through, leaving nothing behind but a few blurry images and technical papers. We were assured it had a clean trajectory, a predictable exit, a clear goodbye date. But that story is no longer holding up because 3I Atlas changed course, and the data now says something far more unsettling. It is not leaving in 2026. Let's be very clear about what that means. Interstellar objects do not behave this way. When something enters our solar system from interstellar space, it follows a hyperbolic path. Gravity bends it, yes, but it does not trap it. It does not slow it down enough to linger. It certainly does not alter its departure timeline unless something unusual is happening. And yet that's exactly what we are seeing. New orbital calculations show subtle but consistent deviations. Not a single glitch, not a rounding error, a pattern that suggests deceleration, course adjustment, and prolonged interaction with the sun's gravity well. In plain terms, this object is staying longer than it should. At first, the explanation sounded comforting, outgassing, jets of gas and dust, pushing it off course. That's the standard answer, the safe answer, the answer we've used for decades. But here's the problem. The expected signatures aren't there. There is no clear cometary tail, no strong plume, no measurable loss of mass that matches the scale of the trajectory change. The forces required to alter this path should be visible. They should be obvious. They are not. So we're left with an uncomfortable gap between cause and effect. Something is influencing the motion of this object, and we do not yet understand what. Now consider this. The revised models suggest that instead of exiting cleanly, 3I Atlas may remain gravitationally bound far longer, possibly shifting into a temporary capture, or at minimum, a delayed escape. That alone is extraordinary. Objects from beyond our solar system are not supposed to do this. This forces a deeper question, not about intent, not about speculation, but about assumptions. What if our models are incomplete? What if we are witnessing a class of interstellar objects we've never properly studied before? What if the universe is once again reminding us that our confidence has outpaced our understanding? History shows this pattern again and again. Every major leap in science began with anomalies that refused to go away. The data didn't fit, the explanations felt thin, and the loudest voices said, "There's nothing to see here." But there was. Right now, we are standing at that familiar edge. 3I Atlas is not behaving the way our textbooks say it should. Its course change is real. Its delayed departure is real. And dismissing those facts would not be science. It would be avoidance. This is not about fear. It's about curiosity. It's about intellectual honesty. It's about admitting that the universe is under no obligation to match our expectations. The most dangerous phrase in science has never been "we don't know." It has always been "we already know." Because right now, one thing is clear. 3 Atlas is rewriting the timeline, and we would be foolish not to pay attention. For years, the expectation around 3I Atlas was simple and reassuring. It would enter the solar system, swing around the sun, and then continue on its way back into interstellar space. That is how these objects are supposed to behave. They arrive with enormous speed, interact briefly with solar gravity, and then leave on a clearly defined escape path. Early calculations placed that exit firmly around 2026. And once those numbers were published, they became treated as settled fact. But orbital paths are not opinions. They are dictated by physics, and physics only answers to data. As more observations were collected, something subtle but persistent began to appear. Each update to the trajectory showed small deviations from the earlier predictions. At first, these differences were easy to dismiss. Slight measurement errors, refinements in instruments, normal corrections that happen all the time in astronomy. Yet the corrections did not cancel out. They accumulated, and when deviations keep stacking in the same direction, they stop looking like noise and start looking like a signal. The revised calculations now show that 3I Atlas is not moving the way a fast, unbound interstellar object should. Its velocity relative to the sun appears lower than expected. Its outbound path is bending more than the original models allowed. The result is unavoidable. The object is no longer on a clean timetable to exit the solar system in 2026. This is not a dramatic claim, it is a mathematical one. To change a predicted departure date by years, even slightly, requires real forces acting over time. Gravity alone should not be enough. The sun can deflect a passing object, but it cannot easily rob it of the energy needed to escape unless something else is at play. That something else is exactly what makes the situation so uncomfortable, because the usual explanations do not line up cleanly with what is being observed. The idea that this is simply a standard comet slowing itself throughout gassing sounds reasonable on the surface, but timing matters, magnitude matters, direction matters. The observed change in course suggests sustained influence, not a brief push, and the lack of strong visual signatures raises serious questions about whether such forces are present at the required level. What makes this even more significant is how confidently the original exit date was accepted. Once a timeline enters the public and scientific narrative, it tends to harden. Future data is often interpreted in ways that preserve the original assumption rather than challenge it. But the sky does not care about expectations. When trajectories change, they demand explanation, not reassurance. If 3I Atlas is not living in 2026, then we are no longer dealing with a simple flyby. We are dealing with an object that is interacting with our solar system in a deeper, longer-lasting way than predicted. That alone places it outside the category we thought it belonged to. And once an object no longer fits its category, the real work of science begins questioning the model, not the measurement. When the trajectory of 3 Atlas began to deviate from expectations, the first explanation offered was the most familiar one: outgassing. The release of gas and dust as solar heat warms volatile material beneath the surface. This process is well understood, widely observed, and has been used for decades to explain small course corrections in comets. On paper, it sounds like the perfect answer: safe, routine, reassuring. But science does not work on comfort. It works on consistency between cause and effect. If outgassing were responsible for the observed changes in 3I Atlas's motion, there should be clear and measurable evidence. Jets strong enough to alter a trajectory over time do not hide easily. They produce visible tails, asymmetric brightness, and changes in the object's rotation. They also result in measurable mass loss. None of these signals appear at the level required to explain what is being observed. The problem is not that outgassing is impossible. The problem is that the scale does not match. The trajectory change implies a sustained force acting in a consistent direction. Random jets do not behave that way. They flare, fade, and shift as the object spins. The resulting motion tends to be erratic. What we see instead is a smooth, persistent deviation that looks controlled rather than chaotic. Even more troubling is the lack of a strong dust or gas envelope. Typical comets interacting with solar radiation develop a visible coma and tail, sometimes stretching millions of kilometers. In this case, observations show either a very weak signature or none at all. That absence matters. You cannot invoke powerful forces without leaving powerful evidence behind. Some have suggested that the object could be composed of unusual materials, perhaps releasing gas that is difficult to detect. This idea attempts to preserve the comet explanation by stretching it to its limits, but stretching a model too far does not strengthen it, it weakens it. Each added assumption increases complexity without increasing certainty. There is also the issue of timing. The strongest outgassing effects usually occur near closest approach to the sun when heating is most intense, yet the course change does not neatly align with that window. The deviation appears sustained beyond what simple thermal models predict. That mismatch raises the question of whether we are forcing an explanation to fit rather than letting the data speak. In science, normal behavior is defined by patterns observed repeatedly across many objects. When something falls outside those patterns, it earns scrutiny, not dismissal. Saying it's just a comet becomes meaningless if the object refuses to behave like one. The deeper issue here is not the failure of a single explanation, but the reflex to reach for it too quickly. Labeling the anomaly as normal before it is understood closes the door to discovery. The absence of clear outgassing evidence does not automatically point to a new answer, but it does clearly rule out complacency. When standard mechanisms cannot account for the observed motion, the responsible response is to admit uncertainty, because in astronomy, unexplained behavior is not an embarrassment. It is an invitation to learn something new about the universe and about the limits of what we think we already know. One of the most unsettling implications of the new data is not just that 3 Atlas altered its path, but that the alteration may be enough to keep it nearby far longer than anyone expected. Revised orbital models now suggest a scenario that once seemed almost unthinkable for an interstellar visitor: delayed escape, prolonged interaction, or even a form of temporary gravitational binding. This is not speculation layered on top of fantasy. It is what the math begins to allow once the original assumptions are relaxed. Interstellar objects are defined by speed. They arrive carrying excess energy, moving too fast to be captured by a single star. Gravity can bend their paths, but not easily steal enough energy to hold them. That is why these encounters are brief. A hello and a goodbye written in predictable equations. Yet when velocity drops even slightly, the rules change dramatically. The line between passing through and staying a while becomes thin. That line is exactly where 3 Atlas now appears to sit. The updated calculations show that instead of accelerating cleanly away after solar passage, the object's outbound trajectory flattens. Its energy relative to the Sun hovers closer to the threshold between bound and unbound motion. This does not mean permanent capture, but it does suggest something far more complex than a simple flyby. A delayed escape could stretch years beyond earlier projections, keeping the object within observational range long after it was assumed to be gone. This matters because temporary capture of interstellar objects should be extremely rare. It requires a delicate balance of speed, direction, and interaction. Our solar system is not designed to trap visitors from the stars. When something appears to flirt with that boundary, it challenges the core assumptions behind how we model these encounters. Some might argue that such scenarios exist in theory buried deep in the equations. That is true, but theory also tells us how unlikely they are. When an event sits at the edge of probability, it demands careful attention, not casual explanation. Rare does not mean impossible, but it does mean significant. A prolonged presence also raises new scientific stakes. An object that lingers can be studied in ways a fleeting one cannot. Changes in brightness, motion, and interaction with solar radiation can be tracked over time. Patterns can be tested rather than inferred. In that sense, delayed escape is not just a mystery. It is an opportunity, but only if it is acknowledged honestly. The discomfort comes from what this implies. If 3I Atlas can slow enough to nearly stick around, then either the object itself is unusual or our understanding of interstellar dynamics is incomplete. Both possibilities carry weight. One points outward toward new classes of objects. The other points inward toward the limitations of our models. What cannot be ignored is that the original narrative no longer fits. A visitor that was supposed to glance off the solar system and vanish is now behaving more like a hesitant guest. And when the universe hesitates, it is usually trying to show us something we were not prepared to see. What makes the behavior of 3 ICE Atlas truly significant is not just that it is unusual, but that it exposes how narrow our existing models really are. For decades, interstellar objects were theoretical. They existed on paper, not in data. When the first confirmed examples finally appeared, the models used to explain them were built quickly, adapted from what we already knew about comets and asteroids. That approach made sense at the time, but it also carried a quiet assumption that objects from other star systems would behave more or less like the ones we already understand. 3I Atlas is testing that assumption. Current models rely on a limited set of forces to explain motion: gravity, solar radiation pressure, and outgassing. When an object does something unexpected, one of those forces is usually adjusted until the equations balance again. But balancing equations is not the same as understanding reality. When adjustments become increasingly strained, they stop being explanations and start being placeholders. The trajectory anomalies, the weak or absent physical signatures, and the possibility of prolonged gravitational interaction all point to a mismatch between observation and theory, not a small one, a structural one. It suggests that we may be forcing a diverse population of interstellar objects into a category that was never designed to hold them. This is how blind spots form in science. A model works well enough in most cases, so it becomes a filter through which all new data is viewed. Anything that fits is accepted. Anything that doesn't is smoothed over, labeled as error, or explained away using increasingly creative assumptions. Over time, the model becomes protected, not questioned. But the universe does not care about elegance or tradition. It produces what it produces. If interstellar objects form under different conditions around different types of stars with different materials and histories, then expecting them all to behave like solar system comets may be deeply flawed. Some may be denser, some may be layered, some may interact with radiation in unfamiliar ways. Without acknowledging this possibility, every anomaly becomes a problem rather than a clue. The most important gaps exposed here are not about this object alone. They are about preparedness. We are only beginning to observe interstellar visitors, yet we are already confident in how they should behave. That confidence may be premature. Early data should widen our curiosity, not narrow it. Scientific progress has always followed this pattern. New phenomena are first explained using old frameworks. Then the exceptions accumulate. Eventually, the framework itself is questioned. That moment feels uncomfortable because it threatens authority and certainty, but it is also where discovery happens. 3I Atlas is not just challenging a trajectory calculation, it is quietly asking whether we are ready to admit that our models may be incomplete. And if we are not, then the real anomaly is not in the sky. It is in how we choose to interpret what we are seeing. The greatest risk in moments like this is not misunderstanding the data, but choosing not to engage with it fully. When an object behaves in ways that resist easy explanation, there is a powerful temptation to smooth over the discomfort by insisting that nothing truly new is happening. History shows how dangerous that instinct can be. Again and again, the most transformative discoveries began as inconvenient anomalies that refused to disappear. What defines these moments is not certainty, but courage. The courage to say this doesn't fit, and to resist the urge to force it to fit anyway. Too often, anomalies are treated as threats to credibility rather than opportunities for understanding. They are framed as mistakes to be corrected instead of signals to be explored. But science does not advance by defending its assumptions. It advances by testing them until they break or evolve. The story of discoveries filled with examples where ignoring uncomfortable data delayed progress, unexplained motions, strange signals, unexpected behaviors. Each one initially dismissed as error or noise. Only later did it become clear that these were the clues pointing toward deeper truths. The lesson is not that every anomaly is revolutionary, but that every anomaly deserves attention proportional to its persistence. In the case of 3I Atlas, the persistence is undeniable. The trajectory change holds across independent observations. The lack of expected physical signatures remains unresolved. The implications ripple outward, touching our understanding of interstellar dynamics, object formation, and even the limits of current observation techniques. To wave this away as trivial would not be caution. It would be complacency. There is also a broader cultural dimension to consider. Modern science operates under immense pressure to deliver clear answers quickly. Uncertainty is often treated as weakness, but uncertainty is not failure, it is honesty. Pretending that unresolved behavior is already understood creates a false sense of closure and discourages further investigation. Engaging seriously with anomalies requires patience and humility. It means allowing multiple hypotheses to coexist without rushing to crown a favorite. It means designing better observations, gathering better data, and being willing to revise even long-standing beliefs. This process is slow, uncomfortable, and sometimes controversial, but it is the engine of real progress. What makes moments like this rare is not the appearance of strange data, but the willingness to let that data reshape understanding. Many anomalies fade with better measurements. Some do not. Those that persist become turning points. They mark the boundary between what was assumed and what must be rethought. Ignoring 3I Atlas would not preserve scientific stability. It would erode it. Stability built on unchallenged assumptions is fragile. Stability built on open inquiry is resilient. The difference lies in whether curiosity is allowed to outrun comfort. In the end, the question is not whether this object will rewrite textbooks. The question is whether we are prepared to listen when the universe quietly suggests that our current ones may be incomplete.